Why do some people claim quantum mechanics is incomplete or inconsistent? And how this is tied with the nature of time? In this video, I have outlined briefly the answer for this question. If you'd like to understand more about the theory behind it, please watch my previous video about the algorithm of time, which you are gonna see on the screen and in the description below. To understand the complexity of the problem, we have started with a thought experiment. Imagine a comet collides with Earth, wiping out all civilization. Does time stop? The answer, of course, is no. The universe keeps moving, which tells us that time exists independently of our human perspective. In classical world, Isaac Newton viewed time as a fixed river that flows everywhere, an external parameter which we use to measure the changes in speed or in momentum. When we move to Einstein's relativity, that river isn't absolute anymore. For an astronaut traveling near the speed of light or near a black hole, time ticks differently compared to us on Earth. Time would experience time dilation due to the speed and the strength of gravitational field. But crucially, whether you use Newtonian or relativistic mechanics, time remains as an external parameter we use to measure the change. It is embedded in the fabric of space-time. However, it's an external parameter. It changes with respect to speed or the strength of gravity, but it is an external parameter which we use to measure the change. And things get strange when we enter the quantum realm. When we enter the quantum realm, unlike the classical world or the classical bit, the qubit or the quantum bit can exist in a superposition. So the fundamental unit of information in quantum mechanics or the quantum world is the qubit. And the qubit can exist in a superposition, which means that it can be 0 and 1 or can be partly in 0 and partly in 1 simultaneously. When we prepare a qubit in this state, we create what we might call a quantum bubble. So we are creating a quantum bubble in our classical world in quantum computing. When we move to quantum realm or quantum computing, things get strange. Unlike the classical bit, which we know in our conventional computing, in quantum mechanics or the quantum world, the fundamental unit of information is the quantum bit or the qubit, which can exist in a superposition, which means that it is not only takes 0 state or 1 state, it can exist simultaneously, partly in 0 and partly in 1 state. And when we prepare a qubit in this state, we have created a superposition. We are sort of creating a superposition or a quantum bubble in our classical world. So basically, we are making a quantum box to use in computations. And here where the controversy arises. The equations that governs the quantum systems, the time evolution of a quantum system or the spatial evolution like Schrödinger equation, these equations are time reversible. So it means that you can go forward and backward in time. So mathematically, you can propagate the wave function backward and forward in time perfectly. However, when you use measurement or due to the act of measurement, time is not reversible anymore. When we measure the system, we force an abrupt change, abrupt collapse to the wave function into a single state. To understand this, let's look at this from quantum computing and the quantum information perspective. If you use a quantum computer, you typically initialize a quantum register of a few qubits. For example, in this thought experiment, you can manipulate the quantum state of the qubits using gates. So those gates will follow a specific sequence that potentially might be the steps of your quantum algorithm. So that sequence can correspond to a quantum algorithm. Then time goes from left to right per convention that we use. However, you can still go reverse via unitary operations. So you can go forward and backward because of the unitarity of the quantum system, which also preserves the norm. However, when you perform the measurement in any given basis, like the z or x or y, typically we measure in z as computational basis, the quantum system has collapsed and it is no longer possible to apply a reverse or unitary operation to retrieve the quantum state prior to the measurement. So this is not reversible anymore. The only thing you can do, you can predict with certainty the probability of a certain outcome of the measurement. This probability or the probabilistic behavior is prominent when we repeat the experiment and measure many times. So take the following example. If you have a 2-qubit quantum computer, you can create entanglement using a Hadamard gate acting on the first qubit and CNOT gate which acts on the two qubits, where the first qubit is the control qubit and the second one is the target qubit. The result of the sequence of these two gates will end up with a quantum state 0, 0, and 1, 1 if the qubits are initialized to 0. And this is what we call entanglement, or one of Bell states. So when you measure the system, you are gonna find either the two qubits are zeros or the two qubits are ones. And the reason for that, this is the only available two situations or two configurations where the qubits can exist simultaneously. So when you do the experiment and then you do the measurement, you will find one of these situations. Pair the coefficient or the amplitude next to these states, you will find that you have 50% chance to find the qubits, both qubits are in 0 and 0 states, or both in one state. So if you repeat the experiment many, many times, you will get statistically about like 50% of the time is in the zeros and 50% of the time are in the one states. However, after the measurement, we cannot back forward. The unitarity is no longer there. Before the measurement, you can still reverse the action of the CNOT and the Hadamard gate. However, after the measurement, this is done. The quantum property is no longer there and the unitarity is no longer helping in going backward in time. Here it comes the perceived inconsistency. The system is reversible before the measurement, but this creates one-way street during the measurement. This was why some people like Roger Penrose and Schrödinger himself questions the theory, which indicate that maybe or potentially the quantum theory is missing something. But as we discussed, this isn't necessarily as a logical contradiction. Might not be necessarily a logical contradiction. It might be indication of missing gap in our knowledge of the underlying understanding of the universe. The collapse is simply the result of complex physical interactions with an external apparatus. Furthermore, even without human intervention, quantum states don't last forever. Through a process called the decoherence, if you leave the qubits untouched or a quantum system untouched, if it is excited, not in the default state, the superposition would naturally lose the information and relax back to its ground state over time. So we're still not having full information about the situation yet. And here it comes as a question: what influences the measurement to favor one outcome at a particular time of the experiment or at a particular run? This question, which was put forward by Roger Penrose and others, they tried to answer it by putting forward that some consciousness acting or affecting rhetorically the measurement and help shaping the outcome. This is true. To help answer this question, we need to define the consciousness first and what actually it does mean. It is a human conscience that we mean, or what? Is something physical? Do we have something like physics consciousness? So let's now back a bit to the original example of having humans disappeared from Earth. When we all disappear from Earth or from the whole universe, the laws of physics will remain acting and will remain working, and our planet is very, very tiny spot in the Milky Way galaxy. Even if you are in a different galaxy, you might not even spot it with tools like ours. So the laws of physics and what we comprehend or we see as quantum properties and the laws of quantum mechanics as we know it now will remain in action. And consequently, nature also does make measurements. The particles are being generated and being captured and absorbed by other systems or atoms or molecular systems in the universe. Further, the statistical behavior is not an effect of the measurement process or our consciousness. It is an intrinsic and genuine process in the quantum system. Take, for example, the following situation. If you have a radioactive material, after the half-life time, half of the nuclei will decay. There is no internal clock to tell which nucleus in advance will decay. If you have 100 radioactive nuclei, after the half-life time, half of them will decay. We don't know which one in advance will decay, but they somehow coordinate this. They know among themselves which one I will decay. I'm gonna decay now. So they communicate with one another. And this is apparently there is something that among them which decides this, but we cannot find any hidden variables or anything that couples this. There's a lot of experiments that have been done, and Alan Aspey, together with other scientists, they have performed an experiments to test the hidden variables, and that was not there at all. And this process is not reversible. Whatever decayed, that decayed. You cannot use the unitarity to retrieve it back. So either we there or not, our consciousness will not play a major role in shaping the outcome of a quantum system. There is fundamental properties of the quantum system itself. So that's put forward the question. If our consciousness, as put forward by many figures around the world, is not the one that impacting the measurement of the quantum system, what happens when we act on a quantum register with specific gates? We still live in the quantum bubble. The time is reversible. And what happens that makes the measurement produces time that is not reversible? And now we're back to the classical time where time always moves forward. The answer could be we have incomplete knowledge. Maybe we need some extension to the quantum mechanics or an upgrade to quantum mechanics, or maybe it is like this. Let me highlight one small point. Still, quantum mechanics puts forward a very strange thing. If you combine quantum mechanics with general relativity, you will end up with a model for quantum gravity. The theory of quantum gravity proposes that the space-time itself might not be continuous, because things in quantum mechanics, when you have a bounded particle or a bounded system, the energy will be quantized. So when you combine the quantum mechanics with general relativity, which says that the gravity is just a curvature in space-time that around a certain mass, then by default, this would produce pixelated space-time. So the space is no longer continuous and the time is no longer continuous as well. And then if you have 2 points in time, there is this very, very tiny gap, which is related to Planck's time, where you cannot comprehend the time at all. We are jumpy in these moments of time. We cannot comprehend between, because they are not there. So what will happen to us in this in between, and according to the quantum gravity? The good thing, this time is very, very tiny. It's a time of Planck's length, which you will find on the screen now. So we are not gonna feel it at all. However, that's still there. The same for the space. The space will be quantized. So if you have a meter, that meter will be quantized as well. Okay, now I come to the conclusion of the previous video. Does time have an algorithm of its own? Can we have an algorithm of time similar to the one we see in quantum computing? The conclusion is no. Time doesn't run according to an algorithm. It remains an external parameter that we use to measure the steps of the universe's algorithm. Whether that universe is continuous or pixelated, time remains the same. It flows differently as special relativity and general relativity indicate, and it has this property in quantum mechanics where it is reversible inside the quantum mechanics. You can move forward and backward. However, after the measurement, the time is no longer reversible. So maybe the time holds a key in that, maybe, but according to our knowledge, that's what we have so far. Now the question is, would this impact the way that we do quantum computing? The answer is no, it won't, because we are using the laws of quantum mechanics to prepare and control quantum systems to do computation with. And once we do the measurement, we get some results or output of this measurement, which we correlate and make post-processing with the result that we are looking for. So in a nutshell, the incompleteness or the knowledge gap in quantum world won't impact our quantum computing and the quantum computations. We are still leveraging the phenomenal properties of quantum mechanics to do computations. And when this is combined with innovative engineering solutions, which are done now and put forward by the major players in the market, eventually, in the near future, we are going to have very powerful quantum computer capable of simulating very large quantum systems and doing very magnificent applications. And in the upcoming videos, we are going to highlight some of these use cases in chemistry or in other domains. If you like to explore more about training or videos in quantum mechanics, feel free to check out Molkit's website, our startup Molkit, which we provide software and consulting services for quantum computing, and check the page of iCafe, where we provide training in different fields, including fundamental physics and fundamental mathematics. And together we take you until you arrive to the good knowledge that makes you touch and feel the beauty of the universe and bring and produce and develop very wonderful applications. Until we meet, see you.